So, Jai Hind all students. Today I am going to start a complex topic of your syllabus, that is fundamentals of electronics engineering. Under this subject, I am going to talk about the clipper circuit. Clipper circuits are those circuits, it is one of the example of your PN junction diode, application of the PN junction diode. So, PN junction diode is used for the variety of applications, like it can be used as in the rectifier circuits, it can be used in the clipper circuit, in the clamper circuit, in the multiplier circuits, and many more. So, today we will be discussing that how do we use the diode in the clipper circuit and what are the applications of the clipper circuits. So, clippers, what is clipper? Clippers are the circuits that are able to clip off or remove a portion of the AC input signal without distorting the remaining portion of the signal. That means, if this is your input signal and if you are passing it through some clipper circuit, then the output will be, something you may able to clip off a portion of the input signal or a portion of the negative half of the signal. Means you may remove this, you may remove this, or you may remove the complete half cycle, positive half cycle, or the negative half cycle, depending upon that how do we connect the diode in the circuit together with the other elements. So, as a clipper circuit is basically consisting of three components. One is the diode, another is the resistance, and third is the DC battery. So, the battery can be optional, it can be there or it cannot be there. So, there are basically two types of clipper circuits which we are going to study, that is the biased clipper and unbiased clipper. So, unbiased clippers are those clippers which are having only two components in the circuit, that is the diode and the resistance, and it will clip the complete half cycle, complete positive half or the complete negative half cycle of the input signal. So, the simplest example of the clipper circuit is half wave rectifier. So, half wave rectifier, depending upon the direction of the diode, it may remove the positive half cycle or it may remove the negative half cycle. But if you would like to remove only a certain portion, like we did in this case, like here, if you want to remove only this portion or if you want to remove only this portion, then we need to connect one more component in the component in the circuit, that is the DC battery, and depending upon the orientation of the diode and the orientation of the battery, we are able to remove a portion of the either positive half cycle or the negative half cycle. So, there are basically two types of the clipper circuits, that is biased clipper and unbiased clipper. Then we further divide these biased and unbiased clipper as the positive clipper or the negative clipper, depending upon if you remove the positive portion of the input signal or removing the negative portion of the input signal. There are, generally we categorize the clippers into two main categories. One is the series clipper and another is the parallel clipper. So, series clipper are those clippers in which we remove a in which the diode is connected in series with the load resistance, whereas parallel clippers are those clippers where diodes is connected in parallel with the load resistance. So, basically we are going to discuss the two types of the clipper circuits, that is the series clipper and the parallel clipper. So, this is the first example of the series clipper, and which is unbiased clipper circuit. Why it is unbiased clipper? Because here we can see that we are having only a diode and a resistance, and there is no additional batteries connected in the circuit. And also this is your series clipper because your diode is connected in series with the load resistance. So, this is the input signal. So, let us start the analysis of this circuit. This is the input signal which we are applying at the input of the circuit, and so in the during the positive half cycle means 0 to T1 time period. So, for the time period 0 to T1, this is, let me mark this terminal as the A terminal and this is as the B terminal. So, here during the first positive half cycle, that is 0 to T1, your terminal A will be at the positive potential and B will be at the negative potential. So, this will make your diode as the reverse bias, because we know if we connect the cathode of the diode to the positive terminal, it makes the diode as a reverse bias, and this diode is ideal diode. So, if we forward bias our ideal diode, it will offer 0 resistance when it is forward bias, and it will offer infinite resistance if it is reverse bias. So, in the first half cycle, your diode is in the reverse bias condition, because diode is reverse bias. So, diode is reverse biased and it will be off. Off means open circuit. So, if it is open circuit, then output will be equal to 0. So, V naught is equal to V naught will be equal to 0. Now, coming to the negative half cycle, that is T1 to T2. So, during T1 to T2, the terminal, your terminal A will be at negative potential and B will be at positive potential during T1 to T2 time period. So, under this condition, diode will be forward bias. It will offer you 0 resistance. So, that if your diode is forward bias, it will be short circuit, and if it will be short circuit, then output will be equal to input. So, if I draw the output waveform just adjacent to the input characteristic, then we can say that during 0 to T1, output is 0, and during the negative half cycle, output will be equal to input. So, this is your negative clipper. This is your negative clipper circuit. So, if I flip the diode in this circuit only, then instead if I write the diagram, draw the diagram like this, I have flipped the direction of the diode in this circuit. So, here during the positive half cycle, your diode will be forward bias. So, output will be equal to input, and during the negative half cycle, this diode will be in a reverse bias position. So, diode will be in off state and output will be equal to 0. So, that will be your positive clipper. So, this is interesting to see that only the orientation of the diode will change the overall phenomena of the circuit. Now, coming to the next circuit, this is, we can say, this is we can see that this is your biased series clipper circuit. Here in this case, I can see that your diode is in a is in series with the resistance, together with a battery, additional battery is connected. That means it is a biased circuit. So, let us start the analysis. So during the first half cycle, here we can see that our diode initially at t is equal to 0. Initially, that means at t is equal to 0. When you are not applying any input signal, what happened? This negative will make, this negative terminal of the battery will make your diode as the reverse bias diode. So I can say, and this diode is considered as the ideal diode. So ideal means it will means the barrier potential has been neglected. We are saying that the time diode will be forward bias, it will offer you 0 resistance, and it will be, if it is reverse bias, it will offer you infinite resistance. So now initially your diode is in a reverse bias state, that means it will be open, so output will be equal to 0. That means up to what value it will be 0? That means up to voltage, that is V volt, this diode will be in a reverse bias mode. So I can say, if I'll draw the output waveform, so I can say that initially diode is in a off state and output will be 0. And when up to which value it will remain 0? Till the time this input Vi is less than V volt, your diode will be off. If diode is off, then output will be equal to 0. Output will be equal to 0. And so this is the value I can say V volt, that is the transition voltage. So up to this value, this is the transition voltage. That means up to this value, your diode will remain in the off state. So I can say this is the time when your diode is 0, because up to this value, our signal, input signal is less than the transition voltage. And as soon as your Vi is greater than V volt, that means during the time period, let's say T1 to T2. So during time T1 to T2, Vi is greater than V volt. So diode will be forward bias. Diode is on, and if your diode is on, then it will be short circuit. So we can write the KVL in this loop. So we'll write the KVL in this loop. So it will be Vi minus V minus V naught is equal to 0. So this will give you the output V naught is equal to Vi minus V. So during time period T1 to T2, your output will be equal to Vi minus V volt. So this will be your output, and this is nothing but Vi minus Vi minus V volt. Now coming to the time period T2 to T3, again during the time period T2 to T3, again your Vi is less than V volt. So diode is off. So output is equal to 0. So I can say that during this time period, again my output will be 0. You can see we are drawing the waveform at every instant of time, because every instant of time the position of the diode is changing, means sometimes it is forward bias, sometimes it is reverse bias, depending upon the input voltage. If the input voltage is greater than your transition voltage, then diode is in a on state, and if it is less than transition voltage, then in that case diode is in a off state. So, now coming to the next half in the complete negative half cycle, that is T3 to T4. So, during the time period T3 to T4, again your Vi is less than V volt, and this will make your diode off, and if diode is off, your output will remain 0. So this is your output voltage. So here we can see that only we get the output during the time period T1 to T2, and that output will be equal to Vi minus V volt. This is the another circuit. If you look at carefully this circuit, here we can see that the orientation of the diode has been changed. Diode is flipped now. In the previous circuit, we have connected the anode of the diode to the battery. Here we have connected the cathode of the diode. So, for the first half cycle, initially if I will say, initially your diode is in a forward bias state, because the battery has its negative terminal to be connected to the negative cathode of the diode. So, which is making your diode forward bias. So, initially we can say diode is on or forward bias. That means it is on. So, if your diode is on, again this diode is considered as the ideal diode. So, if your diode is in on state, then it will be forward bias, and if it is forward bias, then we will write the KVL in the slope. So, if you write KVL, it will be Vi minus V minus V naught is equal to 0. So, what will be my output? V naught will be equal to Vi minus V volt. For making this problem more simple, let us take some numerical value. Here I am taking this Vm as 10 and this is minus of 10 volts, and let us take this value as 2 volt. So, in this, initially if I will start at t is equal to 0, at t is equal to 0, your output will be equal to Vi minus V volt. That means, if Vi is 10 volt and V is 2 volts, then V naught will be equal to 8 volts. That means, at t is equal to 0, your output will be equal to 8 volts. Now, we keep on increasing this voltage. So, as soon as your voltage is crossing this 2 volts, then what will be the, sorry, it at this point of time, I am sorry, here at initially if I am saying initially diode is a forward bias, that means this Vi should be equal to, this Vi should be equal to let us take this Vi is equal to 0 and this is V volt. So, if I am keeping this value 2 volts, V that is 2 volts, then minus of 2. So, my V naught is equal to minus 2 volt, and this is the time when your input signal is at 0 value. So, I can say my initial value is minus 2 volt. It is minus 2 volts. Now, if I keep on increasing this input signal here in this direction, so as soon as my input voltage increases, my Vi, I can say that my Vi is greater than V volt. So, as soon as this input voltage is greater than this battery potential, then your diode will be reverse bias, because the positive potential of the battery or the positive value of the signal will make your, it will supersede this value of 2 volts and it will make your diode reverse bias. So, diode is reverse bias, it means it will be open circuit, and if your diode is in open circuit state, then output will be equal to 0. That means I should draw this here. So, I can say this is your transition voltage V volt. So, till the time your Vi is less than this, then diode will be in a forward bias state. So, if I keep value 0, it will be, output will be equal to minus 2 volt, and if I keep my Vi is equal to 1 volt, let us say this is the value I am taking, then if I keep the value 1 volt here, then output will be equal to minus 1 volt. It will be minus 1 if Vi is equal to 1 volt. So, we get this another point, and if I keep the value Vi is equal to 2 volt, then V naught is equal to 0. So, that means you get this graph. Here you can see this is the graph. So, up to this value when t is equal to 0, when signal was 0, you get the minus 2 volt. If t is equal to minus 1, you get t is equal to plus, at t1 is equal, at time t1, if you have the value, let us say 1 volt, then output will be equal to minus 1 volt, and if you give the input 2 volts, then at that time you get the output equal to 0. Now, as soon as this Vi as soon as this Vi exceed this value, that means if Vi is greater than this V volt, then diode is in a reverse bias state, it will be open. So, your output will be equal to 0. So, output is 0. Kab tak? T1 to T2. And after that, again during the time period T2 to T3. T2 to T3. Your diode is again Vi is less than V volt. So, diode is on, and if it is on, again you get V naught is equal to Vi minus V volt. So, again you get the same signal as you get here 0 to T1 time period. So during T2 to T3, again you get the output, that is V naught is equal to Vi minus V volt. Now coming to the negative half cycle T3 to T4. So during the time period T3 to T4, this terminal will be at negative potential and this will be at positive potential. This negative and this negative, these two voltages will come in series and these two together make your diode forward bias. So during entire negative half cycle T3 to T4, your diode is in a forward bias state. So diode is on. If your diode is on, then again we write the KVL. So if you write the KVL for T3 to T4, it will be minus Vi minus V minus V naught is equal to 0. So V naught will be equal to minus of Vi plus V. So if I consider Vi as the maximum value as 10 volt and V as the 2 volt, that is a fixed battery, then output will be equal to minus of 12 volt maximum. So at this point of time you get the value maximum 12 volt, which is minus of Vi plus V volt. So this is the output waveform. So these are the various series clipper circuits. Out of these, two we have already discussed, this I have discussed, this I have discussed, this I have discussed, also this I have discussed. So let us study these two diodes. First is the positive terminal of the battery is connected to the diode. So let me take up another problem. Let us take this value as the 5 volt. Here I am connecting diode like this, a resistance, and let me take this as the silicon diode, and here let us take the signal. This is, let's say, 20 volts and this is minus 20 volts. This is Vi and this is T. So let us see how do we start the analysis. So initially at T is equal to 0, at time T is equal to 0, we can see that because of this battery, diode is in a reverse bias state. So diode will be reverse bias state till the time this voltage overcome this 5 volts. So as soon as your diode is exceeding, during the entire positive half cycle, this terminal is at positive potential, this is at negative potential. So during complete entire positive half cycle, we can see that this positive terminal together with this positive terminal making your diode as the reverse bias. So I can say that for the complete half cycle 0 to T1, diode is off. Off means it is open circuit. So output will be equal to 0. So, I can say that for the complete positive half cycle, output will be equal to 0. Now, coming to the negative half cycle. So, during the negative half cycle, this terminal will be at negative potential and this will be at positive. So, this negative will try to make your diode forward bias, but what will be the transition voltage? We can see that the 5 volt is required to overcome this 5 volt battery, and also 0.7 volt is required to overcome the barrier potential or the depletion region of this diode, because in this case we have considered diode as the silicon diode. So, I can say that my transition voltage is 5.7 volts. So, I can say that during the time period T1 to T2, T1 to T2, diode Vi is less than 5.7 volts. So, if it is less than 5.7 volts, diode will be off. So, your diode will be off. So, output will be equal to, it will remain 0. So, it will remain 0. But as soon as during the time period T2 to T3, during the time period T2 to T3, your Vi is greater than this potential, that is 5.7 volts. So, as soon as your Vi is greater than 5.7 volts, your diode will be on, and if your diode is in on state, that means it will be replaced by a battery of 0.7, and if I will write the KVL here, so my KVL will be minus Vi plus 5 plus 0.7 minus V naught is equal to 0. So, V naught will be equal to, take out minus sign out. So, Vi minus 5.7 volts. So, if you give the voltage 20 volts in this, so output will be equal to how much? It will be 14.3 volts minus. That will be the maximum value. V naught max. That means at this moment of time you are going to get your output. And again after T2 to T3, T3 to T4, again your Vi is less than 5.7. So, again I can say during the time period T3 to T4, again my Vi is less than 5.7 volts. So, diode will again off and output will be equal to 0. So, this is your output waveform. So, this is so here you can see in this circuit we get the same output, that is minus of Vm minus V, as we have discussed just now. So, this is how we can find out the various outputs of the clipper circuits. So, this completes your the one complex topic. I would like you to solve the various problems, and if you get any kind of doubts, then we can discuss in the live classrooms also. Thank you.